Hello, Jafar.
Hi. How are
Welcome to HIAF.
Thank you.
So you work on creating semiconductors?
So we do the design
Yep.
and we do the testing. Manufacturing is happening overseas, actually.
Yeah.
The challenge is when we have to apply these semiconductor chips in high radiation environment.
Yep.
An environment like in a space or some application in medical physics or let's say in a particle physics experiment, the Large Hadron Collider at CERN is a great example. The radiation gonna damage the commercially available semiconductor chips. That's why they have to be designed particularly for high radiation environments.
I guess everything's so small that one bit of damage is enough to damage a bit or a byte. Or
Exactly. You have to imagine that the size of the single transistor is about the nanometers, and each single chip has billions of transistors on a single device.
Yeah.
So one particle, which can be a proton or heavy ion, can damage the transistor, and as the result, disrupt the functionality of the semiconductor chips.
Right.
Yes.
So the commercial ones are not very resistant.
No.
Are you making ones that are better?
Yes, exactly. The commercial ones are designed to operate in normal environments, so there is no radiation hardening solution or incorporated in the design. So what we do is designing custom radiation hardened chips that can function in high radiation environment without any disruption.
How do you do that? How do you make it more resistant?
So first of all, you have to understand the physics beyond the effects of radiation on semiconductor materials. Then you start from then, you design the simulation framework, and then based on that understanding, you design chips based on novel architecture that can detect and mitigate the radiation effects on the chip. As part of this process, well, design is the first step, and then we manufacturing the chips, we test it in a lab, but then we need to test it in high radiation environments. So we need to simulate the radiation type that we're gonna get in the real application, and to test the chip under that type of the radiation before the application, the real application in the particular system.
Right, and that's what you're doing here.
Yeah, exactly. So particle accelerator machines can generate the same type of the radiation as present in space. So they can generate high energy protons and heavy ions. These type of radiation, they cause the main damage on semiconductor chips in space on a satellite. So what we do as part of our work, we bring our prototype here in this facility, and we expose the prototype under the radiation. It can be high energy protons or heavy ions type. And then in the real time, we detect what's happening on the chip to make sure that the chip can tolerate the target amount of the radiation, well, based on the application in space, based on the mission, before that we deliver that chip to the company or organization.
So this chip today is going into space, or it's a prototype for ones that will be in space?
Yes, the chip today in particular, we developed it for the Department of Defense. The testing and the design had been finalized, manufactured. Now we do the testing under the radiation, and after the testing we can deliver it to the defense and claim that it can be radiation hardened for a space application.
So it actually has smarts built in a way, you said, that compensate for any damage that happens, is that right?
The radiation hardening solution are both in the design of the single transistor, so at nanoscale level. So we shape the transistor in a different way as normal shape of the transistor, in a way that can tolerate much more under the radiation. And also we work at circuit level, at architecture level of the chip itself, that using type of redundancies or other type of the methodology that can detect and mitigate any kind of radiation. And we have different type of the radiation on electronics. So we have target each of them separately in the design.
Right.
Yes.
Are you sort of simulating having a month in space or a year in space, or?
So that's a great question. Now, based on the space mission that we are targeting, the electronics on the satellite get a certain amount of the radiation. So we get the same amount of the radiation using the particle accelerator machine, but in a very short time.
Right.
So what a satellite gets in 4 years' time, here we get it in 1 day.
Right.
But in terms of the total dose, it's the same dose as the satellite gonna get during the mission.
What sort of satellite are we talking? Is it just a CubeSat or is it a?
So it can be applied in any kind of satellite, as far as we are talking the same type of the mission in terms of the altitude and the duration of the mission.
Yeah.
So once we target, for example, low orbit satellite, the chip can go into any kind of satellite for low orbit mission.
Right. Okay.
Yes.
Yeah.
Another type of application for radiation hardened electronics is in defense. In defense, radiation can be used intentionally to target electronic system. And that is an emerging threat in defense environments under the direct energy weapons. So we also work with the Department of Defense to make sure that we can design electronics for Australian defense that can tolerate if the radiation used intentionally to target both defense or civilian electronic systems.
Right.
So that's another example of the application
Yeah.
of radiation hardened electronics.
Yeah. Okay.
Yeah.
But also for, you said, working in medical physics or at the Large Hadron Collider?
Yes. Well, my background comes from particle physics. I was working for the Large Hadron Collider for 5-6 years, and there again, the total amount of the radiation that the Large Hadron Collider is getting is very high. So it's 1,000 times more than a satellite gets in a long-term mission.
Right.
Therefore, dealing with that amount of radiation for particle detector is very hard. So I was part of the a team of large number of people to design semiconductors for the particle detectors can tolerate that amount of the radiation.
So this is at the collision point and bits are going out in all directions?
Yes, exactly. At the collision point, they have the particle detectors around of the collision point. They call it inner detector. And the amount of radiation there gonna reach up to 100 megarad, which is a lot.
Yeah, yeah.
And so designing electronics can tolerate that amount of radiation is very critical for the whole experiment.
Yeah, okay.
Yeah.
All right, amazing stuff. All right, thank you very much and
Thank
good
you.
luck.
Thank you.